Good morning, Vijay. This is a lovely Friday evening, and I'm going on the walk on the road today because the trees in the garden have been cut off to an extent which exposes the garden from every direction, and it actually does feel pretty weird when I'm just walking around there alone with no trees to cover me. And it just feels like I'm a freaking maniac talking into the camera. So here I am. So I finally finished BoJack Horseman, and I think it is the greatest show that I have ever seen. Period. I mean, it's pretty much up there, pretty easily. But today, I don't want to talk about BoJack Horseman. I am gonna talk about the final lectures, 6 Not So Easy Pieces. I finished that too, and that has been an amazing time. Like, I learned properly, like from the very essence of it, what special relativity means and what general relativity means. Like, I actually know now, you know what I mean? And if you actually want to know, then you really should read that book. He explains it very well. I think there are 2 things which are required, which I would tell you to do. There is one video called the Noether's Theorem by the Looking Glass Universe. You may know that channel, and she mentions this Noether's Theorem, which we'll talk about later, and the Minute Physics series on special relativity. He has made a series of videos on that. Like, I can now literally just write everything. Like, it's the physics thing where I can now actually derive everything. Like, I can derive Einstein's work now. Like, that's the level on which I have actually understood it. Like, okay, so not on the mathematical level, in the sense that, like, I cannot do it for all 3 dimensions and time at the same time, like all the 3 like all the 3 physical dimensions. I cannot do it with that because mathematics gets too complicated and I don't know that much mathematics. But I can do it for a single dimension and a single physical dimension and a dimension of time. I can do it with that. Like, I can actually write the equations as well, everything. Like, I can just do it all. And I mean, only for normal, like, translation laws, like laws of movement, you don't even need the first 2 that I'm gonna say. But for other things which I'll tell you right now, you'll need these 2. But with these 3, you can completely transform all of Newton's work into the more correctly defined Einstein's work, right? Which is the special relativity. So we've got 3 things. One of them is conservation of mass, conservation of energy, and the constancy of the speed of light, right? You need only 3 things, and you can write everything. Like, you can derive everything. Okay, so originally my plan was to just explain everything and try to tell you everything in a word, in words. Gonna explain you everything, like the derivation process, but I think that's just not gonna work. That'll be too long and it won't be as much fun. You should, if you're interested in that, you really should just read the book. But I can tell you about the repercussions of just these 3 things on the laws that have already been given by Newton, right? And it's that, of course, if you start moving, then your clock is gonna tick slower. Okay, time is slower, everything that happens is slower. And I guess what I can do is only for that I will give you the explanation for law, which is right here. Okay, so let's say that there are 2 mirrors that are facing each other, right? Like that and like that. And this setup is moving at the speed u in this direction. Okay, so if there is light that is bouncing back and forth at the same point every time, that is this point and this point, as it moves forward, it's gonna look something like this, right? It's gonna go like that and then back up as obviously these move ahead, right? This point is this point basically, because by the time light reaches over here, you know what I mean, this thing is gonna reach here, right, at the amount u. So this is how it's gonna look when this thing is moving in a spaceship that is this thing is in a spaceship that is moving with the speed of u. Now, if you are standing outside of it, right, this is what you're gonna see. But if you're inside of the spaceship moving at speed u, this is what you are gonna see, right? You're just gonna see two plane mirrors like that, and the light bouncing off the points in this way, like that, just like that, right? And just up and down and up and down, just like that. Yeah. So now, because the thing is that the speed of light is constant no matter what speed you have, it means that even in the spaceship, light is gonna bounce back with the speed of c over here as well. And if this distance is this distance, which if we take approximations, it's gonna be about the under root of c square minus u square, right? So if let's say light reaches from here to here in 1 second, right, then it's gonna then this is like c meters, right? We can say this is c meters, and this is less than that, right? This is less than the 3 lakh kilometers per second, whatever. This is gonna be less than that, which is this distance. So light is actually moving through this distance with the speed c, but the distance is less than that. So the time has to be slower as well. You get it? And so everything is gonna be slower, like literally, because if light is going through here, then like if let's say this is a clock, then we can literally say that this clock is ticking slower as it counts the seconds, like 1, 2, 3, because every time it clicks over here, a second passes, right? But a second won't pass here. Even though a second passes over here, a second cannot pass over here because the distance is c square minus u square under root. Just in case it's not clear, the idea is that on the spaceship, what you're gonna be seeing is the light traveling always at speed c. This is the thing that we know is true, right? And the distance that it travels is c square minus u square divided by the time that it takes, which means that the time is equal to under root c square minus u square divided by c. And this is obviously less than 1 second, right? And which means that this ticking is less than 1 second, even though this ticking is 1 second. So outside of the spaceship, 1 second passes, but inside of the spaceship, c square minus u square under root divided by c amount of time passes, which is less than 1. Okay, so you just saw how why time dilation is necessary when you're moving, right? And that is just because the speed of light is constant, as we saw, right? There is also length contraction, which happens because of the same reason. And now when you add in the conservation of mass, you get that, of course, mass must also increase when you're moving at high speeds, and it will increase up to infinity when you approach the speed of light. And the last thing is that when you add the conservation of energy into the mix, you get E equals mc squared. So basically the gist is that when as the energy increases for a system, like if a system starts moving, its kinetic energy increases, right? So what happens is, for conservation of mass and other things to work, and conservation of energy, of course, to work at the same time on that object with respect to other objects, it's necessary that energy also has inertia, right? And as I just said, like the mass increases when an object starts moving. You can say it's because as its kinetic energy increases, energy will have its own inertia because E equals mc squared, and in that relation the amount of kinetic energy that it gains, you can calculate the moving mass or the added mass because of that energy, and that is the mass that which is the proportion which increases when an object is moving. So basically you can also do all these things that, if we also assume that the speed of light is constant and that E equals mc squared, we can also derive things like we can derive everything else. Like we can assume E equals mc squared, and we can derive that mass must increase and time must dilate and all those things. And if we take that mass must increase due to the conservation of momentum and conservation of energy, we can derive that E equals mc squared. So it's a duality in that way, basically. I guess that's just one thing that I have with physics. I of course had for a long time, but it's like if somebody tells me something like this, I just have to know why that's true, and I have to know the derivations, and just I know it now. You know what I mean? Like I actually know what Einstein is all about, and I don't think there is any other pleasure greater than finding out the contents of Einstein's head. And yeah, I think this is a very nice spot. Don't you agree? On the top of the railway tracks. Oh, right. I just realized you might not even know that this place has been made. I don't know if when you were here this was built, but there is this entire walkway that has been built on top of the railway tracks, in front of our railway station. And this is actually a very lonely space, like in the sense nobody's gonna find you here. So I guess I'll shoot videos here because the wind is amazing. You get to see trains, and you're at an elevated position and you're alone. This looks like the perfect place to make some videos. You can find the new bridge from here, the bridge that was in construction when you were here. You can see that from here. So I did recently just finish BoJack Horseman, but I also finished the Feynman's book just after that. So I was just really immersed into that. Like I read that book like a freaking textbook. Like I was 3 days fully immersed into that shit. Like from morning till evening, I was just reading that. I'm not kidding. Like I actually did that. I wrote saw it like a textbook. For 2 or 3 certain points in time, I actually took out my notebook and wrote some shit. Like this was really like a full exercise for me, this book, and I'm just glad that I read it. So thank you so much for this book as a gift. It was really more than worth the price of the book. So thank you. And that's pretty much it. I'll see you on Tuesday.